Oh. We'll open up the door. Thank you. All right. I'll update the grade book. Well, it's 12:10, so let's start it. Yeah.
It's like, wait, what? It's like, how? Is that already this time?
All right, well, welcome. So I hope you got the email today. I decided to make today the last day. So we'll go over the science of the core today. That is a good lecture because it kind of ties everything together from the semester. And the last question, the final exam review, we will talk about today. So if you going through that, this question right here, we'll cover that today. So no lecture on Thursday, although I will be down in my office during class time if you have any questions. Normally I just sit there and just do nothing, so come on in and I'll help you if you want some help studying. So our final exam is a week from today. So after today, time to get into gear on reviewing those chapters, 9, 10, 11, Science of Core Stability. So in addition to the final exam review, I have provided you with another study guide, just similar to the other exams. You can see listed here. Please make sure you look that over. The exam won't have any trick questions. Just what you see on the study guide be the best study tool. So the anterior posterior serape connections. Posterior serape is covered here. But you also want to be familiar with the anterior one, and so we'll talk about that today. Anything else? Any other questions? Okay, all right, so let's jump in. So science of core stability. Okay, so introduction. Past research has demonstrated the effectiveness of core stability interventions for preventing injury and low back pain. Some research has demonstrated direct performance benefits for athletes. The core and core stability lack consistent definitions in the literature. So if you if you look through any of the reviews or papers that have been written on this topic, there's a lack of consistency. And so we know in science it's important to have consistency in the definition, so you can communicate with other professionals effectively. And there's currently no criterion assessment for core stability, so there's no global assessment. We have lots of assessments that indirectly assess core stability in one way or another. So it's a multifaceted concept, and there's still a lot to be done in terms of defining it and how to train it and to test it. So with today's presentation, we'll try to define, based on the current literature, what is the anatomical core, what is core stability, why is it important, what biomechanical and neural mechanisms create core stability. So this is important to understand exactly what are the systems in place that allow us to stabilize this key part of the body. And then if we can understand what it is, then maybe we can test it, right? How can we assess core stability? So just taking some assessments that are out there that kind of get at this concept. Hopefully there's more stuff coming that will be better over time. So as the field evolves, we can determine how to better assess this characteristic. So what constitutes a core stability exercise? So maybe we need to define that. And so once we know what it is and how to test it, how can we train it? And how do we program exercises to improve core stability? So what do we know so far? Okay, so what is the anatomical core? So I would like to throw out a definition to you about what is the anatomical core. So I posit that it's the lumbopelvic hip complex. Lumbopelvic hip complex. So that, as you know, that describes a skeletal segment that's connected together. So the lumbar spine connected to the pelvis at the sacroiliac joints, then the hip joints connected to the pelvis, and all of this is like a chain. Okay, so each of these segments affects the other segments. So this would include all the muscles that affect or control this region. Hey, Bailey, welcome. And all the other soft tissues, so cartilage, ligaments, tendons, and so on that affect motion or stabilization of these segments. So we can see just a few of the muscles here. This would be from a sagittal view, things that we've looked at before in this class in terms of muscles that create a force couple to tilt the pelvis back. So PPT stands for posterior pelvic tilt. The rectus abdominis pulling up on the front of the pelvis, and then the hamstrings and gluteus maximus pulling down on the backside. So the analogy here is the pelvis is like a steering wheel, and so you have these muscles that act as couples that tilt the pelvis backwards. In the same way, we have muscles that act as couples that tilt the pelvis forwards. So with the feet planted, the erector spinae working with the rectus femoris acts as a couple to tilt the pelvis forward. So if we were to study the frontal plane, we would have the same relationship, muscles that tilt the pelvis side to side, and we also have muscles that work together to tilt the pelvis in the transverse plane. So what is core stability? So we know what the core is, so how do we stabilize this? So core stability is the ability to effectively react to postural disruptions. So we've got this muscle activation, and we've got forces that try to disrupt our posture. We can say balance or equilibrium. So things like gravity, okay, we're always dealing with gravity. In addition to gravity, we can be carrying loads. Okay, so how many of you have ever lived in a downstairs or upstairs apartment, and you remember those move-in days when you're trying to carry something that's really awkward upstairs or downstairs? Okay, so yeah, you can relate. Carrying loads places a lot of stress through this lumbopelvic region, and so to avoid injuring those soft tissues of our low back, discs and cartilage and ligaments and so on, we have to create effective muscle activation. Or contact forces in some cases. So some sports involve that. So an analogy I was talking about last week, the ship analogy. So think of the spine as the mast of a ship, and we have all these guy wires that attach at different angles to the spine. On the posterior side of your torso, you have 5 layers of muscles. So that's amazing to think about all the different alignments and orientations. Think about the mast of a ship out on the ocean in stormy seas, dealing with winds from different directions. Just like our bodies, we don't always deal with force from the same direction. So there's not necessarily one most important core muscle. They're all important depending on the type of force, the direction of force. So usually what happens is it's a combination of muscles that are activated to effectively stabilize the spine. And so they're all important. So we have to train or learn to resist forces through different planes of motion to create core stability. So the importance of core stability. So the first one has to do with a platform. So it's a base, it's foundation for applying force. So the center of your body has to be nice and stable, immovable, so that our limbs can produce greater force and power. So we say the proximal stability, in other words, stability in the center of our body, immovable in the center of our body, creates distal mobility. So that has to do with our arms and legs. So we're stable in the center, and then we're more effective in the movement of our arms and legs. So the middle of our body, the core of our body, represents a link. It's a bridge between the upper and lower extremities. Applying force would involve concentric muscle actions. So think of acceleration. So applying force all through our body, transferring force from the legs across the core, which is the bridge, to the arms. Very important. Also as a platform for controlling force. Okay, so we not only produce force against other objects that are external to our bodies, but we also absorb force. And so that's important from an injury prevention standpoint. Being stable and immovable and balanced, we avoid putting excessive stress on our spine. So isometric actions are probably the most important, because when we talk about bracing, remember we looked at some articles a few weeks ago about bracing. That's an isometric action. We're resisting rotation or resisting movement. So we're absorbing force by being more stable. The last one, the third function, protection of the spinal cord, nerve roots, and vital organs. Okay, so sports performance application. So we push against the ground, and if you've had biomechanics, you know about Newton's third law. So you push against the ground, and then the rate and magnitude of force into the ground is reflected through our bodies. And so our body is a series of skeletal linkages that we define as the kinetic chain. So skeletal segments that are linked by joints. And so we transfer energy from the ground through our bodies, this kinetic chain. So if we have any weakness or instability, we get what we call energy leaks. And so if we have a weak link in this kinetic chain, we get energy leaks, and then muscles and segments have to compensate. Okay, so we have movement compensations that happen because we have a weak link in this kinetic chain. So it's likened to a flat tire. We don't want our core to be like a flat tire. We want it to be nice and stable and reactive to effectively transfer force from the legs to the arms. Okay, so I'll include a couple of good quotes in here from good articles that have been written the last few years. You can always see anything in the presentation you can see cited here at the bottom. So a good quote from Santana, 2015. Many of these muscles and tendons, okay, so referring to the core, do not connect directly to bone, rather they connect to one another, transmitting force along pathways ranging much further than simply the length of any one muscle. So it's more complex than just thinking of an isolated muscle that has a point of origin and a point of insertion. Muscles are connected to each other. Muscles work together, they're activated together. They transmit force between each other like a highway system. So if we look at some of the early work on this concept, we have fascial connections. So muscles connected by connective tissue. So the core represents a junction or an intersection for force. So that's a good analogy, an intersection for force. This force is transferred from the legs to the arms. So forces are transmitted along spiral lines from the left side, the left lower extremity, to the right side of the torso, or from the right lower extremity to the left side of the torso. So this is in front, and then in back, it's the same type of concept. So we have from the left hip to the right side of the torso, or from the right to the left, and then from the left to the right. So this goes into that last question on the final exam review. So muscles have connections to each other, tangible fascial connections. So I want you to look at this diagram, and I want you to follow through with me here. So the right gastrocnemius and soleus. So we're going to begin down here, the right gastrocnemius and soleus, right here. And so this all comes from this article from Santana in 2015. So right gastrocnemius soleus to the right hamstrings. Okay, so we're following this path of connection between muscles. And so from the right gastrocnemius soleus to the hamstrings, and then we go to the right glutes, okay, and then we go across, okay, across this pelvic junction over to the left latissimus, and then we're going around the body to the left pectorals. Okay, so is everybody with me so far? So we're here, going up around this way, and then around to the front side of the body, to the left pectorals, which would be right here. Okay, so we went up this way, around this way. Now we're around to the front, which would be this side right here. Left pectorals, right pectorals, so we're right here now. Going back around to the right side of the body right here. So we're going from here to here, and then we're going back down. The right latissimus, left glutes, left hamstring, and left gastrocnemius and soleus. So you see the lines of connection between muscles go up and around and then back down the other side. So I think that's fascinating. As getting away from this concept of just strictly a muscle having two attachment points and isolated contractions for more integrated activation of muscles. So not only pulling on attachment points, but also being connected to muscles that are proximal or medial or lateral to that muscle. So that's the posterior serape. The anterior serape, so the other ones you need to know. So please understand that when Santana put these diagrams in here, he was drawing with the intent of showing the connection more so than depicting the muscle accurately from an anatomical standpoint. So his goal was to show you at the line of action and how it's connected for force transmission. So let's just go through the same process. So the right hip flexors, okay, so that's going to be right here, right hip flexors. And go to the right adductors. So you're following this through. So right hip flexors to right adductors. And then we're going up and across to, let's see, well, not up and across yet. We're still going up. So right internal obliques are right here. And then going across to the left external obliques. So we're going across the pelvic junction. So we're here now. Up to the left serratus anterior. It's going to be right here. And then around to the back side of the body, to the left rhomboid. So that's going to be right here, the left rhomboid. Then over to the right rhomboid. And then from the right rhomboid to the right serratus anterior. Okay, and then back around to the front to the right external oblique, to the left internal oblique, the left adductors, and then the left hip flexors. So just going up and making a loop around the body and back down. So those are the muscles that are connected for the anterior serape. Okay. So why is it important that muscles are connected like that? So here's the reason. This is a really good article if you have a chance to read it. Our library does take this journal. It comes out every other month. Has some great practical application type articles. So by creating a stiffened core, so stiffened core means isometric action, right? Abdominal bracing in a spiral pattern. So you notice the anterior and posterior serape make that spiral pattern. So you're going up and around. The hip and shoulder musculature are anchored together. So the shoulder on one side and the hip on the opposite side are connected by fascia. So that is important for producing forceful arm and leg actions. So this is especially effective for reciprocal actions. So for example, in sprinting, if I have my left arm up and my right arm back, which leg is forward? Yeah, like this, right? And switch like this. So that's what you call a reciprocal action. So it makes sense that those muscles are connected in that spiral pattern. Okay, so the implications for training are to stiffen the torso, so it's abdominal bracing, right? And then once we're braced here, we focus the motion about the hips and shoulders. So let's just consider a few examples. So just a few examples. Polyp press. So how many have done similar? Yeah. Okay, so you're braced, right? And then there's lots of variations where you're holding with arms extended or pushing forwards and backwards. Bird dog. Yeah, lots of you done this to death. Okay, so you're braced in the middle, and then you've got reciprocal action of contralateral arms and legs. Standing cable presses. Okay, so another example of a reciprocal action where the arm that you're pressing with is opposite to the leg that's forward. Crawls. How many have done different crawling type variations? Yeah. Okay, so again, you're braced right here in the middle, so you have effective action of the arms and legs. Suitcase carries. How many of you have done those? Okay, so yeah, you're bracing, and then you're keeping your posture up nice and tall while just holding the weight there at the side. Okay, so sports performance application. So if we go from the wind-up, which in lab we studied that's the preparation phase, right? Wind-up and cocking would be the preparation. Acceleration would be, we'd call that the movement phase, but acceleration is what's happening. And then we have the follow-through phase. So the whole point is, and this again comes from this great article from Santana, is there's little twisting of the core during the entire pitching motion, beginning at the windup. The core is actually stiffened. So that means braced, right? Braced. During the cocking and acceleration phases, this stiffening allows the serape muscle and other tissues to transfer the serape's hip power to the shoulders and eventually the hand all the way to the follow-through. So again, we're stable in the middle, right? And then that enables the hip and shoulders to express greater power output. So again, if you have a chance, it's a good article. Just if you have convenient time, it'd be a good one to read. So more on, this is your day, Corey. More on baseball. Okay, so total body rooting of power in human movement. So the same three phases that we've talked about before: preparation, movement, follow through. Okay, so a left-handed batter will load up the backswing on his left leg, okay, while rotating his shoulders to the left. So let's take that posterior serape concept and apply it. So what you've got right here, left gastrocnemius, right? And then where do we go? We go above to the left hamstring. Okay, so this is on the back of the leg, right? Left glutes. Okay, and then we go across the pelvic junction to where? Across the pelvic intersection over here to the right latissimus dorsi. So you're loading up on the left leg while rotating your shoulders to the left. So this loads up the posterior serape musculature from the left leg to the right shoulder. So as the posterior serape fires from lower left to upper right, okay, so from lower left to upper right, as the posterior serape fires from lower left to upper right. What does it mean, fires? What are we talking about? Muscle activation, right? The nervous system fires up a muscle. It loads the anterior serape from the lower right to the upper left. Okay, once the anterior serape completes contact, okay, so getting ready for the swing here. So left serratus is connected with, right here, left external obliques, right external obliques, right hip flexors, and then right adductors. So we're just following that anterior serape. So once the anterior serape completes the contact phase, the opposite posterior serape decelerates the swing. So we've made contact, now we're in the deceleration phase. And so we're going from on the back side of the body, the opposite posterior serape from the right gastrocnemius, right hamstrings, right glutes, across the pelvic junction to the left latissimus dorsi up here. So just a couple of examples showing how muscles are connected with the posterior and anterior serape. Okay, so another example, just running. You've got what's referred to in this article as the posterior oblique system. So the left latissimus dorsi, the thoracolumbar fascia, which is just this connective tissue over the top of those muscles. So this would be the intersection connected with the gluteus maximus, and the sacroiliac joint is here in the middle. Okay, so we've studied this. Remember the Presswood article? Talked about the Trendelenburg, right? So this position right here is what's being depicted with graphically with this diagram. Okay, so we've got muscles that are pulling the pelvis up on the right side, and then what's the key muscle on the left side that's pulling down? Yeah, well, remember gluteus medius is right. Yeah, from the Presswood article. So gluteus medius is on this side, and you've got obliques and quadratus lumborum on this side that are pulling up. So that creates this force couple that keeps the pelvis level. So if the quadratus lumborum and gluteus medius are weak, especially with the Presswood article, the gluteus medius, okay, the gluteus medius is weak, that's going to allow the pelvis to tilt to the side of the raised leg. So that creates problem. That creates an energy leak. So we're not able to keep the joints aligned. We're not able to push into the ground as effectively if the pelvis is not stable. So remember, proximal stability enables distal mobility. So this just shows that concept. Okay, so unilateral support. So athletes are not always doing skills on both legs. So they have to be effective in balancing on one leg. And so this is where being able to stabilize the pelvis, the lumbopelvic area, is really important. Okay, so injury prevention. One of the key causes of injury is misalignment of joints. So let's take some practical examples here. So here's another great article by Meyer et al. Showing some still frames. So what evidence would we have of poor core stability? So here's the first one. So this is a series of still frames of a drop jump. So what are you noticing there with the knee joints? Yeah, so there's an inward taper there. So we've studied that as let's call that valgus. So that would indicate instability here, which results in misalignment at the knee joints that are distal to the core. Okay, other evidence, the feet are not parallel on ground contact, or the feet do not hit the ground at the same time. That could indicate lack of stability in the core. Okay, so you can see how the feet are not even there or the feet are not hitting the ground at the same time. Other evidence, thighs are not equal side to side during flight in a tuck jump. So you can see this knee is higher than the other there. So that could indicate lack of core stability. Okay, other things, the thighs do not reach at least parallel at the peak of a tuck jump. Okay. Another, excessive landing contact noise. So just slap. Okay, so you can almost tell how effective a jump is by the way it sounds. This is typically displayed by the athlete through landing with flat feet and is typically accompanied by a lack of knee and hip flexion. The other one does not land in the same footprint. What does that mean? Yeah, so how many of you, when you first tried the Just Jump mat, you took off from the mat and landed somewhere else? That's what it means. Okay, so what do we strive for? Okay, so what we want is, if we have any valgus going on, we want to correct that, because valgus here probably means that we've got some pelvic drop here. So isn't it interesting if we correct what's going on in the center of the body, that what's going on at joints that are more distal to that will kind of realign? So the center is the focus. We start there, and then it's a lot easier to get results that are further down the kinetic chain. So what we want over time is this nice neutral pelvis, which means we're nice and stable, and then we get better joint alignment. So things that we do, a lot of you have done lots of this stuff. A lot of it is focused on the gluteus medius. Okay, so we're focusing on keeping our knees out right, because that's what the gluteus medius does. It's a hip abductor. So we're focusing on keeping the hips abducted, which activates the gluteus medius. So a band around the legs with a squat, or a little bit more complicated there's a reverse lunge with the outside leg tied to an upright there to keep the knee out. Some other things we can do, bands are great. I think we've talked about a little bit about this before, but externally rotating the knee joint, so just that proprioceptive cue to turn the knees out. Okay, so how is it that we create core stability? So what is the mechanism? So we have passive tissues, and we also have dynamic tissues that are more active. So passive tissues have a limited role. So we can divide this core stability mechanism into two parts. So the passive subsystem includes tissues that don't contract. So these tissues that basically holds the spine together, the ligaments, facet articulations, intervertebral discs, cartilage end plates, all of these tissues that don't actively contract but provide some stability. The active muscle and neural subsystems have the primary role. So muscles are activated by the nervous system. So more is not always better. So we want the optimal blending of activation and relaxation. So here's a position stand that I wrote a few years ago with some other guys on this topic. Okay, so the spine is most mobile in the cervical and lumbar regions, right? But you already knew that from chapter 11. So why is that we have most of the movement in the cervical and lumbar regions? So one of the things that I didn't mention in chapter 11 is there's a change in the facet joints at the cervicothoracic, so between C7 and T1, so 7th cervical and 1st thoracic, as well as the thoracolumbar junction, so that'd be T12 through L1. So a lot of the movement comes because the facet joints change the way they're oriented at those points. Okay, so we have approximately 1 to 2 degrees of free movement before the ligaments start to tighten up. So we call that 1 to 2 degrees of free movement the neutral zone. So you have that 1 to 2 degrees. If you go beyond that, then you're going to start to get passive resistance. So ligaments are going to start to tighten up to prevent further increases in range of motion. It's a protective mechanism. So this unresisted motion, this 1 to 2 degrees, is called the neutral zone. Okay, so if we go beyond the neutral zone, we have to have stabilizing mechanisms in place. So the passive tissues, okay, they're not able to stabilize very much load. So I want you to take a look here. The osteoligamentous lumbar spine. So that means if we take a spine, a lumbar spine, lumbar part of the spine, and we take away all the muscles and we just leave the ligaments and the facet articulations, how much compressive load could it support? Turns out this particular study right here, 2003, that almost 20 years ago, can't believe that, buckled, osteoligamentous lumbar spine buckled under a compressive load of 90 newtons. So that's a little over 9 kilograms. So that's not very much. So what do we have to have? In addition to all the passive tissues, the muscles. Muscles, we have to have the right amount of muscle activation. So that's why we have low back problems when muscles don't activate properly. When muscles don't activate soon enough, or muscles don't activate in the right combination, then it's up to these passive tissues to stabilize. Even if it's just for a split second, that's long enough for you to hurt and sprain those ligaments. So compressive forces have been estimated to exceed 10,000 newtons during dynamic lifting tasks. So you think about that. If we left it up just to the passive tissues, 90 newtons, that's not enough to stabilize the spine against forces that can exceed 10,000. This is why we have to have the right muscle activation. Okay, so that's when we get to the active neural subsystems. So one of the unique features of the muscles in this area is they're very rich in muscle spindles. So remember, we've studied muscle spindles. Muscle spindles promote reflex contraction. Reflex contraction. So they monitor changes in muscle length. So if a muscle undergoes a really fast stretch, what's the reflex? Contract, right? So if you're walking outside on a day like today and you slip on some ice, you lose your balance and start to fall, you get that reflex contraction, that fast rate of force development to catch you, to restore your balance before you fall. Okay, so it's a neural orchestration. We want not necessarily to be contracted all the time, because how well would we move if we were maximally contracted all the time? Okay, so to move well, we want muscles to contract when they're supposed to contract. In other words, creating the right amount of stiffness, but also to relax, because a relaxed muscle is a fast muscle, right? So it's the optimal blending. So it's the nervous system that does that. Your nervous system is the ultimate multitasker. So it can activate some muscles, it can inhibit some muscles, and then the next instant it reverses its strategy. The nervous system is incredible, taking all of this sensory input from muscle spindles. What's the other proprioceptor? Golgi tendon organs, and creating this optimal blending of stiffness and mobility. So the requirements for stability can change instantaneously. You know that. In sports, in daily life, the spine is under a lot of different demands that can change all the time. So 2003 McGill State, I want you to read this quote to yourself. So is there a most important core muscle? Is there one that should receive emphasis above all others? No, they're all important because the stability requirements can change instantaneously. So the nervous system has to find the right combination to deal with the forces that the body's under at the moment. Okay, so we have a couple of different muscle groups that create this core stability. So we have a local group. There's three characteristics. They're deeply placed. So that means we can't measure it through surface electromyography, right? Because surface EMG picks up the surface. These are more slow twitch, fatigue resistant, postural type muscles. So they have a little bit of activity all the time to maintain our posture through the waking hours of the day. They're very rich in muscle spindles. So what are we talking about? We're talking about tiny muscles that run between adjacent vertebrae. Intertransversalis, interspinalis, rotatorius, we've looked over these in chapter 11. These are like position sensors because they have all of these muscle spindles that are constantly monitoring to make sure the vertebrae are staying in the right position. So we can go from here to here. We can add just a few more muscles. These are also considered to be local. These are muscles that you can't measure with surface EMG. So quadratus lumborum and multifidus. Notice the multifidus runs all the way down the spine on both sides. The quadratus lumborum really kind of gets that ship analogy because it looks like guy wires. It stabilized the spine with this angle on each side. Okay, internal obliques, I would call those a local because you've got what over the top? And external obliques, so it's more local. Okay, and then transverse abdominis underneath that. Transversus abdominis is more horizontal in its fiber alignment. So this is the one we like, and remember the weight belt analogy? This is your weight belt. You've got one. It's the deepest of the abdominal muscles. So if we look at a cross-section of this, we can see all three layers of abdominal muscles on each side here. So beginning with the external obliques, then to the internal obliques, then to the transverse abdominis, around to the front with the rectus abdominis. Okay, and then around to the back, we have the quadratus lumborum, which is right here, and then your erector spinae muscles. So iliocostalis, longissimus, so 2 out of the 3. What's the one missing? Iliocostalis, longissimus, what's the one closest to the spine? Spine, yes, spinalis, good, Lucas. And then multifidus is right here close. You can see we're surrounded on all sides by muscle. This is the third lumbar vertebrae here. So these muscles work together to tighten. Kind of, I guess another analogy would be like a corset. You know what I'm talking about when I say corset? So they tighten around all sides. So they increase the fluid pressure in the abdominal cavity. And that's what creates stability of these spinal segments. So a little more about the transverse abdominis. Acts like a weight belt, okay? Draws in the umbilicus. Okay, so its function, and if you put your hands on your umbilicus, is you can draw your umbilicus back. That's the function of the transverse abdominis, which does increase intra-abdominal pressure to a certain degree. It's also the rehab literature that you see here from Hodges and Cresswell. Research done several years ago showed it was the first muscle activated during unexpected loading of the trunk. So if I ask you to put your hands out like this and close your eyes, and then I drop something in your hands, that's unexpected loading of the trunk. So in unexpected loading of the trunk, you want muscles to activate quickly, because if they don't, and you have all of a sudden supporting weight, that's a recipe for injury. So you have to have very quick activation of muscles in unexpected loading especially. So the transverse abdominis, at least according to this research, was the first muscle to be activated with the body under load. Okay, so the application. As we've seen, and you've read a couple of articles few weeks ago that talked about the importance of abdominal bracing. So with abdominal bracing, we're activating not just the transverse abdominis, but basically everything. So it's a co-contraction of the abdominal wall. And so we teach that because it's so important in being able to produce force in the lower extremities. If we're tight here, that means we're stable, we're immovable, and then force production is a lot better through the hips into the ground. Okay, so abdominal hollowing, because we're only activating the transverse abdominis, it's not the optimal core stabilizing method. Think about it. Any athlete, you're not going to tell them to draw in their umbilicus. You're not going to tell a running back that think about as you take a handoff and you're going through the line, you're not going to say, okay, now draw back your umbilicus. No. Okay, what do? We teach, we want them to brace. Brace for impact. That's the preferred stabilization strategy. Okay, so basic and advanced plank variations, as well as some of those other exercises that were presented early, they're great for teaching abdominal bracing. The crawls and the carries, Pollock presses, all those are great for abdominal bracing. Okay, so you read this article a couple weeks ago, remember? Bracing versus hollowing. Okay, so here's the change in intra-abdominal pressure with bracing versus hollowing. So obviously, if you're an athlete, you're undergoing high forces as part of your sport, you want as much stability as possible. That's going to be the bracing approach. Here's the EMG measurement, the percentage of EMG activation here with the rectus abdominis, external obliques, internal obliques, and erector spinae with each of those approaches, bracing, hollowing, and so on. So here's a follow-up study on bracing versus hollowing. Okay, so what we can see is that when people undergo bracing type training, they get a significant increase in trunk extension as well as hip extension, and also an increase in jump power. Okay, so that's interesting. So you learn how to brace, so you're stable here, and then you're jumping higher over time. So that's a direct transfer from your core. Being tight in the middle means you can apply greater amounts of force into the ground, which is going to increase your jump height. Okay, so that's the local group. The global group, so rather than being deep, they're superficial. So that means closer to the surface. So these are the ones we usually measure with surface EMG. Fast twitch. Okay, so this is where we have some of those muscle cells with the very quick type of responsiveness. Okay, so rectus abdominis right near the surface. Okay. External obliques, also near the surface there. And erector spinae, so sections all the way down. So spinalis, longissimus, iliocostalis is most lateral. So is major and minor. These transmit force from the axial to the appendicular skeleton. So they originate on parts of the axial skeleton, and they insert down here on the appendicular skeleton. So these muscles are especially effective at transmitting force to the lower extremities. Okay, so what about studies that have looked at local versus global? So here's an interesting study done back in 2001. So they evaluated lots of different core muscles, rectus abdominis, external oblique abdominis, longissimus thoracis, and multifidus. They did 16 different exercises. So that's a big study. So in our labs that we did EMG, we did 2 muscles, and we did 2 exercises. So these guys did 1, 2, 3, 4 muscles and 16 exercises. Performed in prone, supine, seated, and standing. The key finding, the multifidus, which is considered to be more of a local muscle, and the longissimus thoracis, which is considered to be more global, more close to the surface, demonstrated similar activity patterns and simultaneous function. So what's the take-home message? The local muscles cannot be activated independent from the global muscles. So just going back to this, there's not a single most important core muscle. Local muscles and global muscles are activated together. Okay, so how are they able to do that? Well, we have a couple different neural mechanisms. Feed forward is pre-planned. So this is anticipatory muscle activation. If you know you're going to be doing something like a jump or a sprint, walking upstairs or downstairs, your body, based on past experience, is going to activate the core muscles. That's feed forward. So anticipatory activation. So this comes from what we call central pattern generators. So these are located in the thoracic and lumbar vertebrae. So these central pattern generators activate these muscles through reflex. So if based on past experience and training, your body's going to activate the core in preparation for activity. So that's feed forward. Feed back happens during or after the movement. So feedback involves fine-tuning. Fine-tuning is important because that increases efficiency of movement. How many basketball, Anders, are you right-handed or left-handed?
Right.
Okay, so when you were like 6 years old, pick up a basketball, and you want to use your right, what was it like the first time you shot with your non-dominant hand?
Probably a little bit backwards.
Okay, yeah. So our body has these feedback mechanisms in place that fine-tune responses over time. So that's an example of a sports skill, but our core is the same way. We don't want too much, we don't want too little, we want the optimal amount. So that's why we have feedback mechanisms that become more efficient over time. So the feedback from proprioceptors, muscle spindles, Golgi tendon organs. You remember some of the names of other ones you wrote an essay about? Pressure sensors. You remember Pacinian corpuscles, Meissner's, Krauss end bulbs. So we have lots of proprioceptors in joints, as well as the ones we always talk about from skeletal muscle. Okay. So another study here. So Kolwicki and Van Vliet utilized a biomechanical model to examine how much local versus global muscles contribute to core stability. So a key point, no single muscle contributed more than 30%. That's interesting. So there's not one most important stabilizer. That's what we keep coming back to. Removal of the lumbar erector spinae, that's a global muscle, resulted in the largest reduction in core stability. So take-home message, just going back to this same concept, both the local and global muscles are important, and they work together. Okay, so McGill in 2003, just to reiterate, all the core muscles are important depending on the context. Okay. So the nervous system controls the core muscles, so we have the optimal blending of stiffness and mobility. Okay. Requirements for stability can change instantaneously. One of the reasons we use unstable surfaces like a Bosu device is because it's good for improving intermuscular coordination. So we'll get back to that and the usefulness of unstable devices in a few more slides. Okay, so if you're looking to maximize strength and power, rather than extreme levels of instability, it's better to shoot for just moderate levels of instability. Anybody, what would you say the reason for that would be? So if you're looking to maximize strength and power, why would moderate instability be better than extreme instability? Yes, okay. What happens to your movement velocity as soon as you're in extreme instability? Okay, good, decreases, which is a good reason, okay? Whereas, what's important if your goal is power? You want to move quick, right? So if you want to be fast, you have to do what? To train fast, right? If you want to be fast, you have to train fast. Okay, so extreme instability wouldn't be the best option in that case because you're lowering movement velocity. What about the amount of weight you can lift? That's going to be decreased as well, so it's not as good for maximal strength. So you have to keep it in context. Some instability is good, extreme instability is probably not so good, especially if you're in a training phase that you're emphasizing maximal strength and power. So just a couple of examples here. There's probably 100 studies that show the same thing, but McBride in 2006, maximal external force output and rate of force development. What's rate of force development? Yes, okay, so it's not just how much force you produce, but how fast you produce force. Is that important for sports? Okay, so you have two cars. Both cars can go 60 miles per hour. Okay, my minivan can go 60 miles per hour. But am I going to enter it in a race? No, because the rate of force, or we could say the rate of acceleration, is the key factor. It's not how strong you are, but how fast you can apply strength that is the key factor. Because sometimes you only have about 1/10 of a second to apply force. Whereas to develop maximal force, it may require 1/2 second. You don't have that much time. So rate of force is really more important than maximal strength. So maximal external force output, rate of force development significantly decreased 45.6% and 40.5% when squats were performed on balanced discs versus the ground. Okay, not saying don't do squats on balanced discs, okay, because there are some benefits. Okay, but if you're in a phase of training where your goal is maximal strength and power, probably not the best approach. So there are training phases where maybe your goal is more on ankle stability and so on, muscle endurance, okay, which when doing squats on balanced discs would be good. So it all depends on the phase of training. Drinkwater, how'd you like that last name? Okay, true. Eric Drinkwater from Australia. Spoken with him a few times. Ground-based free weight squat versus the BOSU free weight squat with a 10-arm load. The BOSU condition significantly decreased concentric power, concentric force, concentric velocity, squat depth, and eccentric power. So again, if your goal is maximal strength and power, moderate instability, ground-based lifts are going to be the best. Okay, so how do we assess core stability? We have a few options, and this part of the literature is growing. So far, existing assessments involve different planes, postures, muscle actions, velocities, and loads. It's probably a good thing. I would hope that at some point we would have a discussion amongst professionals and just come up with one global assessment, but that hasn't happened yet. So the functional movement screen involves some components that would assess core stability, right? So we went through the entire assessment as part of the lab. And then we have other assessments. We'll talk about one of them. So the functional movement screen, as you look through the 7 tests, deep squat, hurdle step, inline lunge, almost all of them, even shoulder mobility, Because in order to do that one thing, you kind of have to be tight through here, even a little bit. So all of them in some way involve different levels of core stability. But it's kind of indirect because you're looking at the whole thing versus just isolating that one part of the body. Okay. All right, so what about some others? So McGill, Canadian exercise physiologist and biomechanist, he wrote this great book called Low Back Disorders, Evidence-Based Prevention and Rehabilitation. So this is what I'm taking from McGill's book. So his battery includes 3 tests. Now, I'm not saying this is the be-all, end-all, I'm just saying it's one of the many approaches. So we need to get together and we need to decide, okay, what is core stability and how do we test it? But until then, we've got a few different assessments. So hip flexion. So those of you, anybody have biomechanics yet? You did? Yeah, you did this. Okay, so we do this as part of a biomechanics lab. So the hip flexion test, you're assessing the endurance of the anterior core muscles. This is the side plank test, so the lateral core muscles. And the hip extension test. So in McGill's protocol, you are held secure, and then your hips are on the edge, and then you're holding this posture for as long as you can. So all these tests are measures of isometric function. So you're holding this posture, and this posture as long as you can. So here are some normative values from McGill's book. So you're looking at men versus women, and then everybody together. So endurance scores. So you think about this on yourself. Healthy college individuals a lot of times don't have difficulty with this, but then you think in a clinical setting, and you're talking about some deficits there. So the extension test, so that's this one right here. So think about being in this position. How long could you hold that position? Just like that without, because as soon as this person drops, that's it. That's the end of the test. Or as soon as the hip drops, that's the end of the test. Or as soon as the back starts to bow or the hip starts to extend, that's the end of the test. So you're holding that defined position for as long as you can. So for extension, the man 161 seconds. Women 185 seconds. Flexion test 136 seconds, 134. And then the RSB, that's the right side bridge. LSB is left side bridge. So you can see the seconds in seconds there. So how do we use this data? So this is again from McGill's textbook. History of disabling back troubles. Over here is no back troubles. So we look at the mean extension, flexion, right side bridge, left side bridge, and then we look at these ratios. Flexion to extension, right side bridge to left side bridge, and so on. Okay, now take a look. History of disabling back troubles. 90 seconds versus 103. Okay, so there's a deficit. 84 seconds on flexion versus 66. Okay, so this is what we want to see because this is from a large population of people without back problems. So what are you immediately seeing over here? What's dominant that shouldn't be as dominant? They have really strong anterior muscles and weaker posterior muscles. So according to this pattern over here, these people are definitely not the same. They're not consistent with these numbers over here, which we could say, okay, if people fall in this range in terms of their ratios and time intervals, that should correlate with no back troubles, right? Okay, especially in thousands of people that McGill has assessed. Okay, versus over here, it looks like the flexors are way too strong for the extensors there. So you look at flexion extension ratio is 1.15 over here. flexion extension ratio. Do you understand what that means? So flexion time over extension time 1.15 versus flexion extension ratio is 0.71. So that stands out like that. So as a therapist, you would look at those and then you try to prescribe exercises to have someone be more consistent with what the no back troubles category would be. So that's the way you use this, and that's the purpose of McGill's book. Okay, all right, so what are some other ways we can assess? So this is stuff that in the field is being talked about. Some potential modalities that we might see in the future. Torso restricted versus unrestricted. So in this case, you're doing a forward medicine ball throw with the torso restricted. In other words, the core is limited because you're strapped in. Over here, you're seated, but you can use use your anterior core in generating that throw. Does everybody understand? Okay, so comparing this versus this, comparing your distance on each would give you kind of an assessment of how much the core is contributing to the movement when you can't use the core as much versus when you can. Okay, backwards medicine ball throw, same thing. Restricted versus unrestricted. Okay, to the side. Okay, so now we're getting into that transverse plane restricted versus unrestricted. These would be fun we should do that. Well, I'm not sure that, I wonder if Dr. Schaefer would allow us to just let loose and throw a medicine ball across the lab. If we had the bench, we could. That would take some people that were brave enough to catch it. Okay, so core exercise definition. What is a core exercise? So we need to define what it is. So McGill in 2003, in his literature review, said that any exercise that channels motor patterns. What's a motor pattern? How would you define motor pattern? So maybe you talk about that in Dr. Schaefer's motor learning class, motor pattern. It's a way that the nervous system activates muscles, we could say. So any motor pattern that channels motor patterns to ensure a stable spine constitutes a core stability exercise. So given that definition, we have a lot of options, right? Any exercise that channels motor patterns to ensure a stable spine constitutes a core stability exercise. So let's talk about prescription then. Okay, so what are some prescriptive principles here? So number one, time under tension. So that's isometric actions. So you're holding a certain posture for a period of time, like a plank, time under tension. How long are you bracing your abdominal wall while in a certain position? Okay, there's also dynamic. So what plane of motion? Sagittal, frontal, transverse, right? Probably more important though is resisting movement, isometrically, resisting movement of the torso. So we'll go through some examples there. Okay, technique factors. So this is the third thing. So basically three things involved here. So unilateral versus bilateral. What does that mean? Yeah, so one arm or one leg. So single leg squat, okay, is a great core stability exercise because if you have an unstable core, it's going to be really difficult to do a single leg squat, okay? Also, lifting a weight with one arm creates greater demands in this area to keep your posture. Okay, moment arm, distribution of the weight, okay? So where is the weight positioned? Further away the weight is from the middle, the greater the activation you're going to have in the middle to keep the body straight. Area and type of base of support. So are your feet close together versus out wide? Which is more stable? Out wide. So naturally you're going to have less activity here. Okay, as soon as you slide your feet in, you're gonna get more activity here. So that's what area means. Type of base of support is the surface. So the ground versus an unstable device like a BOSU. Okay, height of the center of gravity. Okay, so we did overhead squat. So how many of you can overhead squat the same amount of weight you can back squat? Trick question. Okay, no, you can't. All right, so as soon as you take a weight and you put it over your head, that increases the height of the center of gravity. So guess what happens in here? It increases that activity. So overhead squat, you get lots of activity versus the same weight just done like a back squat or a front squat. Okay, so some more information from McGill. Developing core super stiffness. So here's some examples. Multiplanar polyp variations. So this one's probably the most popular. How many of you have done this one? What are we resisting motion through in this? So here, most popular, if I relax here, what's gonna happen? I'm gonna turn, right? If the cable's over here, I'm here, that's, which plane is that? Transverse, right? Okay, here, polyp press, vertical polyp press. Okay, so if he relaxes here, where's he gonna go? This way. So what plane is that? Resisting motion in the frontal plane. So resisting motion through the transverse plane, resisting motion through the frontal plane. How many have done this polyp variation? This one's not done a lot, but it's great. Okay, so he's here, okay, up and down, okay, the cable's back here. If he relaxes his core, what's gonna happen? Go back this way. So what plane is that? Sagittal, right? So we're resisting motion. So we've got proximal stability in our center, and then we're doing actions with the arms through multiple planes of movement. Okay, so what are some other approaches? Super stiffness, that's what we want because proximal stability enables distal mobility. Okay, multiplanar carries. Carries, how many have done a carry like this? That's a great way to develop core fitness. Pick up a barbell and walk with it, okay? How do you have to be if you're doing that? Walking with a barbell overhead. You gotta be tight, right? Braced. That's a great way to develop core stability. Crawl variations, there's lots of those. Dragging a sled in different ways. How does that work? Okay, frontal plane, right? You see the core demands there from the frontal plane. You're braced through here as you're dragging that. Okay, so core stability in the context of strength and power. So if your goal is maximal strength and power, moderate levels of instability. In other words, keep your feet on the ground. What did that study that I did find in highly trained lifters? Remember the one where they did all those deadlifts and squats and overhead press and curls? What was the overall finding in highly trained people? Not untrained people, highly trained people. Was there any benefit to standing on a BOSU? Nope, there wasn't. Findings would be different if it was untrained. Why?
Like the inability to engage your core.
Yeah, untrained people don't have the same ability to engage their core. So there's a threshold. Once you reach a certain level of training, it's probably best to keep your feet on stable ground if the goal is maximal strength and power. So functional athletic stance, that's athletes play on stable ground, so they should probably keep their feet on stable ground. Moderate level of instability, high rate of force, which is the most important thing. Think of a race car. We don't want our bodies to be minivans, we want them to be race cars. High velocity of movement. Okay, so you can do all kinds of things on stable ground. Squat patterns. Think of how many different squat patterns there are. Deadlift patterns, so that's your hip hinge. Press patterns, carries, pull patterns, crawls. All of those can be modified to place more or less emphasis on core stabilizing demands. I don't know why people spend so much time on curls. I mean, if you want good core stability and larger biceps, just pull. That's really the best way. Okay, so conclusions. Not a single most important core muscle. Okay, we want to develop super stiffness. That's isometric fitness in these muscles so we can push and pull with our arms and legs more effectively. Okay, ground-based movements. That's where it's at. You're supporting your body in a functional stance. You get the same type of activation that's present with daily life and sports. Okay, so where do unstable surfaces fit in? They do have a place. Periodized program. Rather than light days, we do unstable days. Does that make sense? Because on an unstable surface, we're generally lifting lighter amounts of weight. So we have heavy days, we have light days. That's how periodization works. Rather than light days, we go with unstable days. So that's how everything fits together. Okay, so that's a semester. Thank you. Let me know if you have any questions.